In this video, we will introduce some non-mathematical functional blocks. The first one we want to introduce here is the max function. So max of x, it means that the x is a vector, which with the element x0 to Sn, and we will pick one of them whose value is the largest value as our output. So in here is the item n. Okay, so you may wonder if we can take a derivative of this function. Yeah, but the answer is yes, we can do that. So, and the result is that we know that the argument here is x0 to Sn, and when we take the partial x of the partial max of x, since the x, you may notice that the max x is an vector, which is Sn here, but not vector, a scalar whose value is xn. And the x is a vector, so the result is a vector whose shape is the same as the x. That's the first thing. And the second thing is that each element in this array is actually partial xi of the partial max of x. Okay, and since the max s is Sn, so it means that unless I is n, the result will be 0, since there is no dependency between the xi and the max of x. So the result will look like this. This is item n, and for others are 0. Okay, so this is the derivative of a max function. So what does this exactly? What's the meaning of this derivative exactly? It's actually that we know that when we want to calculate the partial x or partial L, sorry. When we want to calculate the partial x of partial L, it will actually to calculate the partial z of partial L dot the partial x of partial z, and this is a called the Austrian gradient, and this is the gradient of the function. So this is like this. So it means that only this term will become non-zero. For others are all zeros. So it means that in this vector, the partial L of partial z, we will only pick the item n of this vector as the output. For others will become the 0. Okay. So if we draw it graphically, we have a couple of input here for the max function, and we will only output one vector, which is with the large value. For example, this is Sn, this is Sn, and this will be a gradient of those items. So only the nth item will fall back to here. For others, you will be 0. So for this one, there's 0, 0, 0, s, this item to here, and the others are 0. So this is a gradient of the items of the max function. So actually this makes sense, since if you think about the definition of a directive, it means that if the value changes a little bit, how much the output should be changed. For the max function, unless it is the max function, is the item with the max value, all those items, when they change, you won't affect the output. Only this item will affect the output. So that so if you want to adjust the parameter here, and we hope that they can adjust the loss value, the output. So we only need to adjust the last item. We don't really need to care about others. And for the max function, you may wonder why the one with the max function, the max value might change. Yes, we will change. So whenever you change this value, if you decrease it, and then this will be smaller than others. So in the next for phase, the maximum value, the item with the maximum value will change, and then in the next update, the gradient will fall to this item instead of this item. Okay, so you need to remember that when we say we calculate the gradient and using gradient to update parameters, we are actually talking about the gradient is just for the current value of a for phase. It then so that we can only change the parameters for a little bit, since that when we update the parameters, the gradient will be updated as well. So our assumption is that if we update the weight for a very small portion, you won't change the gradient. So that the update will not change the parameter to the wrong direction. So, but the question is that what's the small enough value, small enough step? There's no standard answer for this. We need to do try and error to figure out the best answer for this value. Okay, so this is a max function. So that in the max function, in the forward, we just call the max function to get the max value of x. But in the backward, we need to broadcast this. We need to calculate, for example, the condition here. We need to figure out what's the item with the max value in here. So this will actually return an array, and which will be the false, and only one of them are true. For others are false, and the false will be 0, 0, and this 1 and 0. So that after we get the condition here, we just broadcast the upstream gradient to all the items whose value is 1. Okay, and for the max, there's only one item with a maximum value. Okay, so this is implementation for the max function, and for the other one is called selection. The selection means that that's a closed entropy. In the closed entropy, we use this formula to calculate the loss of between to calculate the difference between the ground truth and the prediction. Okay, so but since for the 1-hot encoding, if the label is in 1-hot encoding, it means that there's only one item which is 1, for others are 0. So it means that we only, so for this item here, for this dimension here, there's only one item whose value is non-zero, and which is, for example, is u here. So this is UTH item is 1. So there's only one item here will be left in the closed entropy loss. So if we draw it pictorially, we have a couple of different input here, from log p0 to log pn, and we using the select function to select one of item, which is u. For the u is, we will select the item u to be the output, and the u is decided by the label here. But we don't really care about it. We only know that the selection function will just pick one of the input as its output. Okay. So how could we implement the directive of the selection function? Is actually the same as the max. So if we review the case for the max it just pick out the item n, and the item n is decided by all the value of x0 to Sn, and one of the item with the maximum value will be selected. But for the selection, it's the same. We pick out one of the item as its output value, but this time we want using the maximum value, and we use the item whose label is 1 as its selection. Okay, so we can imagine that the implementation of a selection will be very similar to the max function. So actually it is exactly the same. You can compare the implementation of backward of the selection with the implementation of max function. They are exactly the same, because we still compare the value of x data and the y data, and select the one whose value is the same as our selected item, and then we just broadcast the gradient to the selected item by using the broadcast2 function here. So in this way, you may imagine that we could implement something called the if, or called the get item, or called a lot of non-mathematical functions by using a similar way. So for those functions we won't change the value of upstream gradient. We only change the way we flow the gradient to its input variables. And for example, the redo is the other one. Actually, redo is the max of x0. So it means that the implementation should be very close to the max. And then if the x is larger than 0, the value will be selected. Otherwise, it will be 0. So we using this comparison to get the gradient which we need to flow to the input, and then we just multiply the upstream gradient with the mask vector here to get our gradient, the gradient of the redo functions. Okay, and this is the implementation of a sigmoid. I don't explain it in more detail. You can check this link if to see the actual implementation of sigmoid is not using the original formula here. We are using a hypertension to implement the sigmoid because of the numerical stability issue. You can check the discussion in this link for the details. And then there's a lot of other functions is implemented in the D0 framework, and you can check but you can check the link for all the implementations. And if you have any questions about how those functions are implemented, you may send a message to me, and I will try to respond to you in the discussion, or I may produce another video to explain your question in details if it is necessary. Okay, so this is the implementation of the functional blockers in the D0. So we discussed how to do the directives of a lot of functions, a lot of either mathematical function or the structural functions. So in the next video, we'll discuss the layer and the models, so that those facility will simplify the implementation of the neural network.